Welcome everybody to today's webinar, From Data to Information to Decisions, How Can Statistical Graphics Support Clinical Quality Evaluation in Hospitals? My name is Jane Clare and I'm the Education Resource Manager for ISQua, and I'd just like to welcome you all along today and thank you very much for coming. What I'm going to do firstly is I'm going to introduce our speaker, Professor Andreas Becker. Professor Becker is a surgeon and CEO of the non-profit hospital group Clinotel, comprising of 40 hospitals in Germany that take care of over 720,000 inpatients per year. His expertise extends to medical quality, patient safety and medical risk assessment. He is a professor for hospital management in Catholic University of Applied Sciences in Cologne, with the focus on medical risk management and patient safety. Today is going to be a very interesting webinar and I hope that you gain an awful lot from it. With this in mind, I'd like to remind all participants that we will have 3 questions in our fellowship forum following on from this webinar, and in order to gain credit points for watching the webinar, you also have to answer all 3 questions. So without further ado, I'm going to hand over to Andreas and we will start the webinar.
Yeah, Jane, thank you very much for the very interesting introduction. Now I know who I am and what I do. That's very good. So yeah, warm welcome to all of you from the city of Cologne, which is right in the middle, in the heart of Germany. We say, as you heard, my name is Andreas Becker, and today it's really an honor to provide an overview about this topic to you. So, just let's start. First of all, I'll give you an overview about the webinar, what we are going to do. First point would be that you get some management ideas behind the sequence, data, information, and decisions, and what are my management ideas behind this topic. Then you see information about our data. Then I come to some graphs, some examples, and finally, I try a conclusion. But before I start, I would like to point out that you can download an article to this webinar in an English version from the website of our journal, Interdisciplinary Contributions to Hospital Management, for free. It's an open source journal. The article gives an extensive overview of the literature, contains information about additional graphs, for example, timelines and control charts. And you will find checklists and recommendations for the analysis of the graphs and 2 files in Excel with examples how to calculate CASM and VLAT graphs mentioned later in this webinar. In addition, I would like to point out that you can find a full version of, I think, the fantastic speech of Sister Mary Jean Ryan about accountability she gave at the ISQua conference in 2011. And afterwards, we were allowed to print this great speech in English in our journal. So read it. It's really very good. Okay, we start with some management ideas. Clinical processes, from my point of view, form the basis for all the work and activities related to the hospital environment. They comprise the main type of services provided and give rise to clinical diagnostics and treatment with the goal of meeting the requirements of patients to an appropriate extent. The degree to which these requirements are met is generally described in the term quality, with special focus on outcome quality. The management of a hospital or its respective medical business units should first and foremost be aligned to quality with a special emphasis on outcome quality. In context with the aforementioned remarks, effective decisions are based on the analysis of data and information. The sequence of words used in the title of this webinar, Data, Information, Decisions, is derived from this very statement. Appropriate data, therefore, form the basis for our issue-related decision-making, because it is this data that determines how the response is organized. The relevant data on clinical processes and their outcomes can be extracted from routine data, for example. Data here on the left side itself have no value. This is a great misunderstanding in a lot of people in hospital management. They only receive a value in the course of the first transformation stage, whereby a specific piece of recorded data is given a meaning to a qualified member of hospital staff. then data becomes information. For example, a mortality rate or complication rate in percent has no value itself. You need to transfer it to an information to answer the question, is this mortality rate the mortality rate that I expected? How does it fit to my target values, if I have target values, however? The famous scientist Bateson understands an elementary information as a difference that makes a difference, a very interesting definition. And he thus draws our attention to a question it is absolutely imperative that we ask, the answer to which is the starting point for decision making. Typical questions I know arising in the execution of clinical leadership in our hospitals are, for example, in the case of patients with community-acquired pneumonia, CAP, does a deviation of 1% in the hospital mortality rate in hospitals, when considering their comparative data, represent a difference that makes a difference and therefore requires action? Or another question, when the monthly hospital mortality rate of patients with CAP in my unit fluctuates between, let's say, 8 and 12%, can that be considered to be a random variation? Or is it the case of a difference that makes a difference and therefore requires action? In the course of the next transformation stage, a specific piece of information is again given a meaning through a qualified member of hospital staff, and a decision then can be done. For example, you can say we don't need an intervention, or we need for improvement and we have to invest some resources. Be careful. Lilford and co-workers told us in 2004 outcomes are influenced by definitions, data quality, patient case mix, clinical quality of care, and even by chance. That's very important. That means, in the context of our DID process, we have to consider the sources of variance. The transformation process described today, with its focus on a significant difference, is designed to enable issue-related decisions to be made that only lead to intervention when this is really required. It is about, as it is inherent to all clinical processes, determining an indication. That means the pro and contra of taking specific steps in order to improve quality. If there is actually no necessity to take an action, for example, if you think that the above-mentioned fluctuations only refer to random monthly variations, then financial and staff resources may be spent that are then missing somewhere else. In addition, this may also lead to other negative effects. Staff motivation is undermined when they realize that action taken does not lead to desired changes to data. In this case, we see CAP hospital mortality rates. The significance of specific data can be clarified best demonstrated with the aid of graphics. The data set used as a basis for the graphics and charts contained in this webinar comprises hospital administrative case data from about 1.8 million discharges in patients from the years 2010 to 2012 provided by the hospitals of our group. And the data presented now in the following about HMR and CAP patients. We talk about approximately 25,000 CAP patients in hospital treated in the years 2010 to 2012. Here's the first very, very simple chart on the first look. We talk about raw data. Non-risk adjusted hospital mortality rate, the called raw data, based on routine data, can be plotted and depicted in very different ways. One option is to create a bar chart as shown here. Such bar charts form part of our hospital group's standard monthly evaluations. What is illustrated here is the non-risk adjusted HMR data provided by the respective hospitals. These are the black bars, as well as the overall value of all hospitals in the group. This is the gray bar. In our evaluations, of course, the individual bars are labeled with the names of the hospitals for internal quality comparison reasons. The figure shows the outcomes of the year 2012 at December 31st. For an individual hospital, for example here in Hospital A and Hospital B, the question may be asked as to whether the values of 12% or 20.7% respectively correspond with the hospital's expectations, which means a predefined value. That's a management job. This, of course, presumes that such a value has been prospectively formulated, which would be expected of a quality-oriented clinical leadership. When formulating the expected value, it is possible to expect data from the literature, guidelines, external quality sources, or other hospitals. These values can then also be drawn upon when formulating a target value for an improvement process. Attention should be paid to the fact that the sources drawn upon are very likely to be using different data sets and definitions. Already it is clear that conducting comparative quality assessment can be an extremely complex task. It should not be regarded as an exact science. That's very important, since there are a number of impossibilities that need to be taken into account. The overall value of all healthcare institutions in the hospital group provides an initial helpline, this is the gray bar, which in our experience is intuitively applied by the users in the hospitals in a way that they divide this graph, the bar charts, into two parts, to the left and to the right of the group average value. It's a very simple picture of the world, to the left and to the right of the gray bar chart. It is therefore understandable when clinical leaders declare their objective as being to the right of the group value. At first glance, this would appear to be a good thing, since it is based on the robust division to the left and the right of the average group value. It is only when you take a closer look that you realize what this really implies. It is not as positive as you think, since the hospitals to the right of the group value show weights between 5.8% and 13.3%. It would make sense to define one's objective as being to the right of the group value when a hospital participating in this evaluation program for the first time indicates a value above the group value 13.6%. A value of 13.6% or lower might be defined as a tendency and a first step towards improvement, but should subsequently be substituted by a concrete numeric value. That's what we want in our hospital group. The same discussion you can have on the left side of the group value. Hospitals rank between somewhere above 13% and 20.7%. And the question is, what is your personal target for your hospital or for your medical department? Higher hospital mortality rates can thus be explained by the higher proportion of patients with severe CAP and increased morbidity. It is absolutely legitimate to follow this clinical traceable explanatory model to start with. The explanatory model is, of course, from hospitals on the left side. We have the oldest and most sickest patients, most severe patients with CAP. But if we accept this explanatory model, we must not forget to ask whether the respective clinic actually disposes of a data on disease severity and or comorbidity. Without such data, the above explanatory model remains purely hypothetical. Nothing can be verified and no evidence can be drawn upon as a basis to warrant an issue-related, this is to say, educated decision. And be sure, every hospital in our group and every hospital in Germany, I think, might be the same in your countries you're listening from. Everybody has the most severe and the oldest patients. I'm really looking since 25 years in Germany for that very, very special hospitals with the young and healthy patients. We are really looking for it. A further objective in the efforts to improve quality may, of course, also be a shift within the regions to the left and the right of the group value. That's clear, and the respective hospital management or clinical leadership is accountable for determining the exact value. That's what we expect from our hospital managements. Another helpline here is the average value of all CAP patients overall Germany from the year 2011 from the so-called external quality assurance, which means that was 12.7% of all patients. And so you are not only able to decide if you're right or left from the gray bar. Another point you can add is above or below the line from all the German values. So you have some interesting data. You can try to decide where is my position and, of course, what is my target. At that stage, when we talk about what can it mean, what may be the reasons behind my data, we have to do a short excursus to the analysis of clinical processes. A concept that has been proven, or that has proven to be extremely practical and useful for the analysis of the structural process and outcome quality of clinical processes is the so-called analysis pyramid method, which is shown in this slide. The pyramid model recognizes multiple explanations and recommends that the most likely explanations are checked first. Or with other words, investigation should start with data and end with people and with individuals, not please the other way around. That's not good, as Lilford and co-workers pointed out in 2004. It is clear to the viewer that the lowest section of the pyramid forms the basis for quality assessment and thus also for educated issue-related decision-making, since insufficient or poor quality data can quickly lead to misinterpretations. The second level is a call to analyze patient characteristics, which again must be displayed in the form of correct data. Level 3 addresses the structures and resources which can impact outcome quality. The care process in level 4 takes place within the environment formed by the given structures and resources. It is influenced by both these aspects and must therefore be regarded in this context. It is especially important to know whether the care process can be regarded as scientifically proven and is founded on best knowledge and best practice. Has the best possible knowledge, in this case the guidelines about CAP, been adopted by the hospital, and is it being effectively applied to patients? Does transfer research into practice work in this case? Clinical processes involve human resources, and the questions formulated for level 5 are of elementary importance for the quality of the process. Staff whose activities impact fulfilling these requirements in providing services as healthcare providers must dispose over these competences to perform the work. Educational qualifications, training, skills, experience, and so on. It should also be noted that medical staff is occupied within the environment formed by the given structures and resources and other organizational factors affecting the work environment. You'll find further information about the pyramid model in my publication for this webinar. Now we come to the next slide. Again a bar chart, but now with observed and expected values. Slide 8 showed a bar chart with plotted non-risk adjusted hospital mortality rate, you call it crude mortality rate, data. Here we are referring to observed hospital mortality, and the observed rates are also depicted in this slide, again the bar charts, and supplementary by the expected rates of mortality calculated for the respective hospitals. The expected hospital mortality rate is depicted as a filled grade diamond with the corresponding 95% confidence interval, we call it CI. This evaluation is also made available to our hospitals on a monthly basis. The hospitals marked with an X here and here have two low case numbers to enable expected values to be calculated. A quality assessment that takes place and that takes expected values into account should therefore not be carried out in these cases. The observed values for hospital A and B have already been commented above. The expected value for hospital fatality is calculated by using a statistical model which is based on multiple logistic regression analysis in our hospital group. The expected AMR calculated for a patient undergoing treatment increases with the number of so-called risk factors pertaining to the patient. These may be, in case of CAP, primary diagnosis CAP through pseudomonas or aspiration pneumonia, higher age, simultaneously occurring malign illness, condition following a stroke, left side heart failure, stage 4, or chronic kidney disease in stage 4. All these factors increase the risk of dying in hospital if you come to the hospital with a CAP. One can say the older the patients and the more risk factors manifested, the higher the calculated expected hospital fatality rate. For the monthly evaluation, the expected values of all concluded inpatient cases of CAP are accumulated and the resulting value then depicted as a filled grade diamond with the corresponding CI. Even if all hospitals are represented in the chart, the goal is not to stage a comparison in the sense of who is providing the best quality. This display format enables the comparison of the observed and expected values of a hospital. We are now talking again about the self-referential process, whereby each individual hospital can retrieve significant information applicable to its own situation. When considering the expected values of the different hospitals, the question may arise as to why the expected value of one department deviates from that of another department, although the observer knows both departments and presumes that the risk structure for CIP patients in both departments hardly differs, if at all. That is the advantage when you are part of a hospital group, where you can also acquire information on the frequency of risk factors for the patients in other hospitals. Our group ensures this, given that this data is made available to member hospitals every month. The expected value is based on risk factors, and these are in turn, with the exception of age, coded by secondary diagnosis in the ICD-10. This gives rise to the documentation coding expected value sequence, and should there be any doubts about the quality of the data, reference should be made to level 1 and 2 in the pilot model and then relevant questions asked. The confidence intervals indicated for the expected values enable conclusions to be made as to the statistical significance of the outcome. Should the confidence interval not contain the observed value given by the bar chart, this, as a rule of thumb, points to the difference as being statistically significant. In Hospital A, this is the case. Here is the observed mortality rate, black bar, lower than the expected, here's the diamond. And if fewer CIP patients die than expected, this outcome, I think, is also classified as being clinically relevant. This, of course, does not answer the question as to what lies behind this outcome. For example, is it due to overcoding, which has resulted in a wrongly defined high expected fatality rate? Are the clinical diagnostics and therapy in line, perfectly in line with the CIP guidelines? So the width of the confidence interval depends on the extent of the random sampling and standard deviations in the groups under review. A large control sample leads to more confidence and thus to a narrow confidence interval. A broad confidence interval derives from a small control sample, small patient number, and you see it very good in these hospitals here, marked with an X. Very, very broad confidence interval. The greater, we call it the statistical spread of these values, the more uncertain or vague the conclusion will be, and the broader the confidence interval. This is very, very important to know if you try to come to decisions with such data. That's really very important from my point of view. The chart indicates a number of approaches which can be helpful for quality assessment processes. In our experience, this is not sufficient on its own because it always depends on who is reading the chart and what experience or expectations they have. Comments often heard in practice are, in case that observed hospital mortality rate is the same or lower than we expected, which is quite good, this is an outcome that meets the expectations of the hospital managers perfectly. And of course, it infers a course of action or strategy that is in line with best evidence, best clinical practice. If the outcome is the other way around, that means the observed mortality is higher than we expected, this may well be solely due to the coding of the insufficient and unrealistic statistical procedures. By the way, to mention, it's the same statistical procedure used for all the hospitals. A hospital may be treating the most severely ill patients but cannot plot their data correctly using the beams available. In this case, you often hear three responses to data feedback. First, Professor Becker, the data are wrong. Second, then the answer is, sorry, it's your data. Second, the data are right, but it is not a problem. The answer is, oh, I'm very sorry, that's not my opinion. Third answer is, the data are right, it is a problem, but it is not my problem. Nothing. Meanwhile, you can expect my answer. It is important that the following points are communicated to the target group directly interested in a specific evaluation. This applies especially to users with a limited knowledge of statistics or a wrong knowledge. Statistic processes do not claim to depict the truth. This is not possible because the results are quite simple, always affected by a certain probability of error, and depend on how well formulated the questions the statistical procedures are, and of course on the quality of your data. Never forget, statistics in general, and thus also risk adjustment, is the beginning and not the end of the analysis process. So the calculation of an expected risk-adjusted HMR is a prognostic rather than a diagnostic process. Any plotted data that appears to be out of the ordinary is a symptom that requires further in-depth analysis. This is the diagnostic part of quality assessment. Now you see the so-called standardized hospital mortality rate, once again bars. And to calculate this for the individual hospitals, the ratio first is formulated for one hospital observed value divided by the expected value of the hospital, and then multiplied by the observed mortality rate throughout the group. This value then describes the result that would be achievable for every hospital if all hospitals had been treating patients with the same disease severity. That's a very interesting graph. The outcomes for all the hospitals can thus be immediately compared with one and another. Both clinics A and B have obviously benefited from the process. It is evident that hospital B no longer shows the highest value and that hospital A has moved further to the right. This is due to the characteristics of the observed and expected values and requires no further elaboration at this point. This is really one of my favorites, this graph. A very big favorite in our hospital group is the so-called funnel plot. A funnel plot is a graphical aid for really institutional comparison in which an estimate of an underlying quantity is plotted against an interpretable result, interpretable measure of its precision. Control limits form a funnel around the target outcome. Funnel plots enable representation of data and simultaneously take case numbers into account. They serve as a visual aid to detecting bias. The funnel plot contains two so-called funnel limits. This is the first one, this is the second one, which are calculated around the arithmetic mean. This is the horizontal gray line, and correspond to confidence intervals. Presuming that rates deviating from the mean are purely coincidental, there is a 95% likelihood that they will lie within the inner limit. This is between here, and a 99.8% likelihood that they will lie within the outer limit, which is here. It is clearly visible that as the case number increases, the limits are more closely spaced. To ensure the anonymization of data, we here forego plotting the case numbers volume on the x-axis. Normally, for every hospital, you find here the case numbers on the x-axis. All in all, we can say the result displayed in the funnel plot is good, since only one clinic exceeds an upper limit, in this case the 95% limit. This is here. Since hospitals as a rule in Germany are reproached for too high fatality rates, the graph is initially dedicated to healthcare institutions approaching the upper limits. One clinic is plotted as being on the 95% limit, here, and one as between the upper limits, it's here. In both cases, it would be advisable to conduct a further analysis of the outcomes. There are two clinics plotted as lying on the lower 95% limit, here, the arrows. This could be seen as evidence of best practice, since their respective outcomes can therefore not be seen as being randomly low. In both cases, reference should again be made to levels 1 and 2, or up to 5 in the analysis pyramid, and an investigation could be conducted accordingly. In this case, to answer the question, is here best practice, we would like to transfer to all our hospitals in our hospital group. In view of the outcomes recorded above and the comparatively high case number, Hospital A lies, as expected, below the average and close to the lower 95% limit, which is here. The significance of the case number related calculation of the limit becomes evident when you consider hospital B, which lies within the 95% limit. We didn't expect that. From our point of view, there is no contradiction to these values, certain based on the observed and expected and the standardized hospital mortality rates, given that the value for this hospital is plotted very close to the upper 95% limit, and this is a sort of warning for our group. From the point of view of a clinical management, you would assess this finding in the final plot as endorsing values determined above and conduct a further analysis of clinical processes. We call it process audit. Areas, and this is very interesting, with different rates, hospital mortality rates, and similar case volume, we call it outcome clusters, give rise to the question as to what impact structures and treatment processes in the clinics concerned may have on the risk-adjusted in-hospital mortality rate. Such issues can in turn be a reason for benchmarking the structures underlying the processes. In their paper, Dimmick and co-workers showed that it is really fundamental to consider the case volume when evaluating outcomes. The funnel plot illustrated here demonstrates that clinics with lower case numbers show substantially larger spreads of values before they come anywhere near the limits and becoming alarming. At this juncture, it does not really matter whether we are dealing with non-adjusted or adjusted values. You see it here, smaller case numbers, here we are approximately about 150, 160 patients per year, and you see the limits here are more broad. If the goal is to generate serious representation of the relevant data, however, these circumstances should not be regarded as a chance for so-called small case numbers or even small hospitals to avoid being subjected to internal or external quality assessment. It is quite natural for the spread of values to be case volume related, and this of course may lead to a completely different view, which claims that lower case numbers actually complicate data assessment to a large extent. This is because it is very difficult to determine trends or effects of transformation processes, and data can only be assessed with a relatively high degree of uncertainty. This therefore means that clinics with higher case volumes are, at least from a statistical standpoint, in a favorable situation when it comes to data and quality assessment. With high case numbers, much sooner you see effects of what you are changing in time. Now we come to a very, very interesting graph, the so-called variable life adjusted display. VLAD depends on the cumulative sum method, shortly called CASM. The literature available describing the differences and characteristics CASM and VLAD have in common is actually quite confusing. So to avoid further confusion, in this webinar, the term VLAD is used for the portrayal of cumulative sums of risk-adjusted data. In the article to the webinar, you will find an extensive overview about both types of graphs with a lot of literature in the appendix. Ideas on how and when to apply these methods can be found on websites hosted by certain Australian states such as Queensland and Victoria, and this is especially interesting since they include VLAD in conjunction with the analysis parameter, statistic websites. In the graph we see three lines. Two lines represent one upper and one lower limit, similar to the limits you saw in the funnel plot. The colorful line in the middle represents the cumulative sum of the outcome at any given patient or date during the measurement period, which here starts on the 1st of January and ends at December 31st. So each data point in the graph of this hospital, each data point along the curve corresponds to one patient. The curve goes up when a patient survives or a lot of patients survive in a timeline, and goes down if one or some patients die. A line above the zero value at a given date indicates, for example, here, that more patients survived than we expected. We saved lives. Here at that point we see at that special point patient number approximately 160, middle of April, we saved 5 lives, 5 survived more than we expected. A line below the zero value, fortunately you can't see it here in the graph, but the line below the zero value at a given date indicates that fewer patients survived than we expected, then we are in the region of we lost lives. The data from the wheeled graph was calculated for hospital A as follows. The 432 patients are numbered in ascending order according to the date and time on which they were discharged. This is the column-headed patient. The expected mortality is calculated for each patient using the above-mentioned statistical model. This is the column E for expected. The observed outcome, survived, you find in the column O for observed. The outcome is coded as 0, we use a number, if the patient survived, and if the patient died, it is coded with the value 1. You see one patient who died. The difference in the column E minus O, expected minus observed, is then calculated for each patient in the following way. The expected value, as an example of patient 1, was calculated as 1.146. The value can be between 1 and 0, 0 and 100% expected hospital mortality. The patient did not die, 0, and so 0.146 minus 0 equals 0.146. That's easy. So we say, in other words, 0.146, patients, fewer patients died than we expected. The expected value for patient 5 was calculated as 0.253. The patient here died, and we say 0.253 minus 1 is minus 0.747, or in other words, 0.747 more patients died than we expected. In the column headed wheeled, the individual differences from the column E minus O are then added together, adding the values of patient 1 here, plus from patient 2 equals this sum at the time of patient 2. Adding the values from patient 1 up to patient 443 at the end of the year has a final result of 20.883. So for hospital A, this therefore means that in the year 2012, approximately 21 patients fewer died than expected. This was to be anticipated, given that in the former shown figure it was evident that the observed value was below the 95% confidence interval of the expected value. Wheeled graphs are also extremely useful for those looking to translate statistical significance into clinical relevance. Here each data point, as I said before, along the curve corresponds to a patient, thus allowing abnormal or even alarming sections of the wheeled to be allocated to the respective patients and thus also to periods of time. From January to mid-February, for example, the wheeled rises only to drop around mid-March. At this point of time, cumulatively speaking, exactly the number of patients dies as was expected. Here it is along the zero line. And that's the very interesting point of the wheeled. We don't use the wheeled at the end of the year. We started some months before to give our hospital wheeleds for a lot of patient groups every month. So the chance for that hospital would be to see a trend. And then at the end of February, if they get the graph in March, to say, what happened here? What was going on? Did we change our treatment or have we different patients? From mid-March onwards, the wheeled shows a practically continuously rising curve, which naturally gives rise to the question as to whether this rise will eventually become striking in the positive sense. The evidence of such a run of good performance is naturally important since it may provide an indication of good practice. Again, questions arise. What was different during this time period? What did we do especially well, which could be done more in future? Equally important would be the acknowledgement of a run-of-bed performance, since this may develop into a qualitatively insufficient process. In addition, the chart displays two limits, an upper and a lower one. Both limits are composed of data points, which are calculated according to a complex procedure for the current VLAD value. And the calculation of the limits have been explained in detail by a number of competent authors, which is why we will not go into more detail. Here you find explanations in the appendix of my article to the webinar. The limits serve to answer the question as to whether the observed quoted ones are indications of positive or negative abnormalities, or statistically speaking, if they are striking and thus can be interpreted as so-called signals. In our example, the upper limit is set at 30% decrease and the lower limit at a 30% increase in the relative risk. Applying these limits is the earliest possible way to identify signals. The VLAD for patient 2 to 3 at the end of May here is higher than the corresponding value of the upper limit. It thus can be interpreted as a positive signal. It indicates that at this point in the time, cumulatively speaking, more patients survive statistically significant than expected. This is very interesting for the clinical leaders. As soon as a signal is identified, a limit needs to be reset. You can see it here, which means that the limit has to be recalculated and the process can be commenced to identify a further 30% decrease or increase in relative risk. You see this is another time the case, middle of October. A further development of the VLAD I want to show you was presented in a very, very good and interesting open access article by Christina Pagel and co-workers from University College London in 2013. This added more applications whereby individual data points which correspond to individual cases are highlighted in different colors. We have adopted this idea in the development of the VLAD for our hospital group. And the especially innovative feature of the graph is that it allows different colors to use for the data points, and I now show you how we code it. But this would be a proposal to ISQua. I think this could be a very, very interesting web seminar because they talk about a real improvement process and how to use the VLAD. So maybe a good addition to this webinar, if I may say so. On this slide, you see our coding. A green data point indicates that the upper limit was reached, for example here, or that a patient who ranked highly in the individual risk-adjusted mortality actually survived. These are so-called unexpected survivors. And the question is, what did we do there? What happened? What was going very good? A data point is highlighted in red when the lower limit has been reached, or when a patient with a low expected value has died. This could be patients for very interesting case conferences, but you see none of them here in that hospital. Given that we have access to the patient's routine data, we are able to examine the secondary diagnosis of the patients for adverse events, which may be available in the form of coded secondary diagnosis. If there is one or perhaps even several medical events plotted in the graph, the data point is highlighted in orange. The particular advantage of this method is that every data point corresponds to the line of one patient only, and thus any unexpected plottings in the chart can be assigned to the respective patient at specific periods of time. With regard to VLAD, one can say in summary that VLAD does not represent our target value, the hospital mortality rate, as a percentage, but it transfers it as to the number of lives statistically saved or lost at a given point in time. And this, I think, is very interesting. We are not going to talk about percent values, we talk about people, and that's a very attractive target for people working in hospitals, not to say we fulfill checklists and we follow a guideline, but next year we try to save 10 patients' lives in CAP or other diseases, and you can monitor it from month to month. That's very interesting. On the Government of Victoria's website, they sum up this very nicely. They say a key strength is that each episode of care has an impact on the chart. That is, Every patient outcome moves the line up or down according to the outcome. I try a summary, a conclusion. Statistical graphics can effectively support data information decision transformation, as we were able to show from the data collected from 2 hospitals. This involves a complex process, which in turn reflects the complexity of clinical processes. Attempts to reduce this complexity have not proved to be productive. Many observers, especially in Germany at that moment, find it charming to reduce the quality of the care process, a medical department, or even an entire hospital to traffic light colors, thumbs up or thumbs down, or a series of stars. However, one cannot seriously expect that such ratings will promote sustainable improvements of care quality. The time prerequisite for initiating a change in care process is the professional quality of the staff involved. This begins with the data information decision sequence and becomes mission critical when put into practice and maintained as standard practice. It is not only the problem, in this case deviating from an evidence-based guideline, that is maintained through repetitive operational measures. The solution too must be revealed and manifested in new, observable and repetitive operational measures and behavior of people. This requires a lot of energy, which people are only prepared to invest in on a long-term basis if the complexity of the work they perform and the conditions under which they do so are acknowledged. If the solution does not take the form of a repetitive operational measure or behavior, it will not last long. This is the effect described in practice when external consultants come up to with a solution, install it and withdraw. Since in such cases it is often about the consultant's solution and not the solution of those directly involved in the care process, metaphorically speaking, the consultant takes the solution away with him when he leaves and the process returns to its former state. Dixon, Woods and co-workers provided a very, very interesting open access overview over the success factors that determine successful clinical relevant change processes. From my opinion, this is really a must-read article. It is open space. Further analysis, as well as the clinical diagnosis process, should be carefully planned and conducted in a target-oriented fashion. We recommend using the aforementioned analysis pyramid. Besides collecting and analyzing process-relevant data, we recommend 2 further measures which in our experience can deliver important findings with regard to quality evaluation, prevention and quality planning. It should be mentioned here in this context. These are morbidity and mortality conferences and so-called process audits, which can be both the trigger and the consequence of the data information decision sequence. You'll find more information about the MLM conference and the audit in the paper to this webinar. The procedure described today supports clinical leadership in the evaluation of clinical processes with respect to process and outcome quality. The knowledge, which is a prerequisite. We think from our point of view to go the way like this and to handle it like this, that we can say from the point of view of our patients, the time gained can indeed make a difference. That makes a difference. And now, ladies and gentlemen, it's time to say thank you very, very much for your attention, and thank you very much to ISQua for the opportunity to talk to an international audience. Thank you very much.
Thank you very much, Andreas. Well done. That was a really, really excellent webinar. There was a huge amount of information in that. It was very, very detailed, but also tremendously interesting. So thank you very, very much for your contribution. We just have one question in from Ahmed, and that question is, if the VLAD is 20, does this mean risk is not accurately estimated?
That's a good question. Very good question, Anna. Thank you for that. So, if you use risk assessment models, there are quality parameters that give you the answer, how precise is your model. So, if at the end we see a good result for the hospital, then we know how precise the model is, and for me it's not important to say is it exact 21 or might it possibly be 22 or 23, but that's the range we are working on. Our model is very, very precise. If we say the VLAD is the start and not the end, and this is what we are just doing with our hospitals, we go to the hospital and we look for best practice. We know the data quality. We are, every 4 weeks, we check data quality of all the hospitals, and we know on level 1 in the parameter we have no problem. And then we ask what is going on. Until now, the VLAD was correct. Doesn't matter if it's plus or minus 1 or 2 patients. It's the trend that's interesting. And the medical leaders say that's a great tool we can monitor during the year, and that's the important point.
Super.
But we need a good model, of course.
Yes, yes, you do. Well, listen, that's the only question we had in. I think there was so much detail in that, Andreas. I think everybody will have to maybe have a reread over it, have a little bit of a think about it. And certainly if any of the participants have any questions, they can email them in and I will forward them on to Andreas and we will get back to you.
Okay.
So just leaves
me
to say thank you very, very much, Andreas, again, for that huge contribution. And thank you very much for our participants also for taking part. Super. Thank you very much, Andreas.
Okay, bye.
Bye now. Thank you.